Next problem is maximize is equal to 5x1 plus 8x2 subject to 3x1 plus 2x2 greater than or equal to 3, x1 plus 4x2 greater than or equal to 4, x1 plus x2 less than or equal to 5, and x1 x2 greater than or equal to 0. Here there are two variables, three constraints. Now convert the problem to canonical form by adding slack, surplus and artificial variables appropriately. Since the constraint 1 is of the type greater than or equal to, we should subtract surplus variable s1 and add artificial variable a1. And as the constraint 2 is again greater than or equal to type, we should subtract surplus variable s2 and add artificial variable a2. And the third constraint is less than or equal to type, we should add slack variable s3. The standard form of LPP becomes maximize is equal to 5x1 plus 8x2 plus 0 into s1 plus 0 into s2 plus 0 into s3 minus ma1 minus ma2 subject to the constraints 3x1 plus 2x2 minus s1 plus a1 equal to 3, x1 plus 4x2 minus s2 plus a2 equal to 4, x1 plus x2 plus s3 equal to 5, and x1 x2 s1 s2 s3 a1 a2 all greater than or equal to 0. From the initial simplex table, basic variables are a1, a2, s3, and the coefficients of these basic variables in the objective function are minus m, 0, and CJs are the coefficients of x1, x2, s1, s2, s3, a1, a2 in the objective function, and other values we can write from the equations. Then calculate Z value, that's equal to sigma CB into XB, that's equal to minus 7m. Zj values, that is sigma CB into X size. So we can calculate the values in that row. Then calculate the net value Cj minus Hj. Then if the values are less than or equal to 0, the solution is optimal. Otherwise, find the maximum positive value that corresponds to 6m plus 8. So the corresponding variable x2 will be the entering variable. Calculate the minimum ratio using the rule xb by x2 where x2 greater than 0. We can see that the minimum value is 1 and the corresponding variable a2 will be the living variable. Then the intersection is 4, that is the pivot element. Then using these information we can find the next iteration. For that we use these new elementary row operations. This will be the second iteration table. Here the basic variables are a1, x2, s3, and the coefficient values are minus m, 8, 0. Other values we will get from the elementary row operations. Then look at the net values Cj minus Hj. Here also the values are not less than or equal to 0. That means we had to again improve the solution. Look at the leaving variable and entering variable. Here the entering variable will be x1, the leaving variable will be a1. The intersecting value is the pivot element, it is 5 by 2. Then to form the next table, make this 5 by 2 1 and all other elements in that column 0. For that we can do the elementary row operations. The elementary row operations are new r1 equal to old r1 into 2 by 5, new r2 equal to old r2 minus 1 by 4 into new r1, and new r3 equal to old r3 minus 3 by 4 into new r1. Now we will get the third iteration table, and similar to the previous table we can find living variable, entering variable, and evaluate the net values, and we can see that the net values are again not less than or equal to 0. That means we have to improve the solution. That means we have to form the next table. Here the pivot element is 1 by 5. So make this pivot element 1 and all other elements in that column 0. For that we can use the new elementary row operations. The new elementary row operations are new R1 equal to old R1 into 5, new R2 equal to old R2 plus 3 by 10 into new R1, and new R3 equal to old R3 minus 1 by 10 into new R1. This will be the fourth iteration table, and from the table we can see that the net values are again not less than or equal to 0. So we have to improve the solution. Find the living variable and entering variable. Here the living variable is 3, entering variable is S1. Then the pivot element is 1 by 2. Make this pivot element 1, all other elements in that column 0. So do again the new elementary row operations. Then the new R3 equal to old R3 into 2. New R1 equal to old R1 plus 2 times new R3, and new R2 equal to old R2 plus 1 by 2 into new R3. Based on these elementary row operations, we can form the next table. Then the fifth table is shown here, and the basic variables are S2, X2, S1. The corresponding values, coefficients are shown here. And we can see that from the net values are less than or equal to 0. That means we reached the optimal solution, and the optimal solution is x1 equal to 0 and x2 equal to 5. And the maximum value is equal to 40. Since one of the basic solution is 0, that corresponds to the degenerate solution.